Ever wondered how businesses forecast sales or predict future trends just by looking at the past data? In this video, we will talk about forecasting models such as ARIMA and Holt-Winters and how to build them in Python. If you're new to this channel, I'm Karina. I have transformed my career from finance to data, and now I help others to do the same one step at a time. Let's build some machine learning. In this video, I will be using data I found at kaggle.com, link in the description to this video. First step, we need to import required libraries, and there would be many of them. Let me quickly explain what each of those libraries does. First one is pandas, and we need it for data handling and manipulation. With pandas, you are able to read your CSV file. The next module we are uploading is NumPy. It is our go-to library for numerical operations. Next one, we need to upload matplotlib, pyplot to visualize our data. We will create different charts to see how our data looks like. The next one is a datetime module, which helps us work with date and time data. And this module is critical for organizing time series, which we will be working with today. Then from our stats models, we need to import AddFuller and ARIMA. AddFuller is ADF test, or also called augmented decay-Fuller test, that checks if our time series data is stationary or not. And our ARIMA model is the model we will be working with today. The ARIMA model is a powerful statistical model used to forecast future values based on past values. Then we need to import ARIMA, which is a tool that automates the process of finding the best parameters for our ARIMA model. From sklearn metrics, we need to import mean squared error and mean absolute error, which we'll be using for evaluating the model performance. Also from stats models, we need to import a seasonal decompose. This is a function that breaks our time series down into trend, seasonal, and residual components. Also from stats model Holt-Winters, we need to import exponential smoothing and simple exponential smoothing that we will be using for our Holt-Winters model. Let's execute this part. If you get an error that some of these modules is not found, you probably need to install those modules on your machine, and to do that we say !pip install and then the name of the missing module. For example, I had to install PMD ARIMA, so you might need to do the same. So first you run this code and then you run the code that imports the modules. Next step, we will upload our file, we will read our file. We say def or data frame equals pd.read_csv brackets in the brackets path to our file. So my file is called trained4, that's the file I downloaded from kaggle.com. And we will also print head to see top 5 rows of our data. That's the data set we have. For our time series analysis, we don't need all this data. All we need is order date and sales. At the end, we just need 2 columns we will be working with. Let's quickly check .info to see what data types we have. Okay, it's all object. So since we will be working with order date, we need to convert our order date from object format to date time. To do that, we say df square brackets order date equals pd.to_datetime brackets, and then we are referencing to the column we are converting. In our case, it is order date, and then we indicate what format we will be using. I'm using European format where it's day, month, year. As I mentioned before, we will be working with only 2 columns. That's why we need to resample our data to monthly. So we need to get total sales per month. I'm creating a new data frame called monthly sales equals df.groupby brackets in the brackets it is pd.grouper brackets key equals order date frequency me, and then in square brackets sales.sum brackets. If you look at our data at our order date, we have sales by day. So we have 8th of November, 12th of June. By using the grouper, you group all the data at the end of the month. We say frequency me means month's end. So all the data will be displayed as 31st of January, 28th of February, as of month's end. By saying key equals order date, you're saying to the grouper that we will be using the column order date as the basis for our grouping. And then, of course, square bracket sales, we say that after grouping by month, we are selecting only sales column to aggregate. And how we want to aggregate it? We want to sum it. Let's then print our monthly sales head just to see how this new data frame looks like. Now all our data is displayed as of month's end, so total sales at the end of the month. For visualization of our data, we will be using matplotlib library. So we say plt.figure fig size equals 12 by 6. This way you're selecting the size of your figure, height and width. Then we say in plt.plot to plot our data. What we are plotting? We are plotting our monthly sales. As a label, I will use monthly sales. Then we can select title, X label, Y label, and say if you want legend or not. plt.show to see to display our visual. You can see our sales very spiky. We definitely have upward trends, but at the same time it fluctuates a lot, which is hard for making predictions, but we will use this data anyway to build our two models and see how they cope with this very spiky, very uneven sales trend. Now we will do time series decomposition, and decomposition separates the data into trend, seasonal and residual components. This helps identifying underlying patterns in a time series. We need to say decomposition equals seasonal decomposed, brackets what we are decomposing, monthly sales, and model for decomposition we use additive. Then we say figure equals decomposition dot plot brackets, figure set size inches 14 by 10, that's we selecting the size of our visuals, and plt.show to display these decomposed charts. So you can see the first chart is our sales, then it decomposed our data into trend, seasonal and residual. This is our trend. As we saw, it does have these upward trends. It's growing year by year. Now we can see our seasonality. Fast fashion brands as H&M, Zara, they all have very serious seasonality because you have 4 seasons. So at the end of each season, you have sales of that season. You also might have some mid-year sales or Black Friday sales. So your sales graph will look like that. And every year it will actually repeat. You hope that your trend is upwards, so you sell more, but at the same time you can see the same fluctuations year over year. So when we perform this decomposition, we have this last chart, which is the residual. And residual represents the random fluctuations or noise that remain after removing the trend and seasonal component from the original time series. This is essentially the part of the data that the model couldn't explain with the trend and seasonal patterns. The next step, we will create a little function to check our data for stationarity using augmented decay-fuller test. Stationarity in time series means that the statistical properties of the series, such as a mean, variance and autocorrelation, remain constant over time. Generally, stationary data is more predictable and easier to model, especially with time series like ARIMA. Augmented decay-fuller test is a statistical test used to determine if a time series is stationary. And how it works, we create a null hypothesis. Our null hypothesis is that the series has a unit root and is non-stationary, and our alternative hypothesis, the series is stationary. So with our function, if the p-value is below a chosen significance level, which is commonly 0.05, we will reject our null hypothesis, indicating series is likely stationary. And with a critical value, it is thresholds 1%, 5% and 10%, and it helps us to translate the ADF statistic. If the ADF statistic is less than the critical value, it suggests that data is stationary. To create a function, we say def and then the name of our function, brackets, and then we say time series, then colon. Result equals add fuller time series. Then we will print several lines. The first one will be augmented decay-fuller test result. Then we print ADF statistics. We print in our p-value, our critical value, and then we say for key value in result for items, we print key and value. Then we need to return our result and check if it's less than 0.05. And then we create a variable called isStationary and check stationarity brackets monthly sales. And then we just print in the results. So let's run it. We printed the results of our test, and the test concludes that the time series is stationary. So it's supposed to be easier to predict and easier to create forecasting models. And because of that, we can use a ARIMA model. Now it's time to create our ARIMA model. So first of all, we are creating this auto model, which equals auto ARIMA, and we put the next parameters: monthly sales, stat P, stat Q, max P, max Q, seasonal true, D none, trace true, error action ignore, suppress warnings true, and stepwise true. And now I will explain what each of that means. Monthly sales is our dataset that we are passing into our after ARIMA. P and Q are parameters for ARIMA model. I forgot to say what ARIMA stands for. ARIMA stands for autoregressive integrated moving averages. P and Q are parameters of ARIMA, and P is autoregressive order, which represents the number of lagged observations in the model, while Q is moving average order, representing the number of lagged forecast errors in the model. Start P and start Q set the initial value for P and Q to 0. ARIMA will then increase these values to find the best combination up to max P and max Q. And we set our max P and max Q to 5. This defines the maximum values that P and Q can take. M12, this parameter defines the seasonal period of the data, indicating that the data has a yearly seasonality or 12 months. And this means that the algorithm should look for patterns that repeat every 12 months, which is very common for retail companies, for example. We say seasonal equals true. This enables the seasonal ARIMA or SARIMA model, which considers seasonal effects. If we say seasonal equals false, our ARIMA will fit a standard non-seasonal ARIMA model. D equals none. D is difference in order, and setting D equals none allows ARIMA to automatically determine the optimal difference in level needed to achieve stationary. We've done our test, we know that our data is already stationary. Trace equals true displays the progress of ARIMA, so you will see what is happening to your model. Error action ignore. If a parameter combination fails to converge or produces an error, our ARIMA will skip it without stopping, allowing the search process to continue. Suppress warnings true. This suppresses warnings during the search, reducing unnecessary output, especially if there are numerous warnings from different models being tested. So you know those red warnings, we will not see them because we will suppress them. And stepwise equals true enables a more efficient search strategy by using a stepwise approach to find the best parameters. Instead of testing every possible combination, it follows a smarter path by adding or removing parameters iteratively based on performance. Let's run this bit. And now you can see the process is displayed. And now we found what will be the best model for us. Now we are creating our model and fitting the results. So first of all, we say model equals ARIMA, brackets. In the brackets, we say monthly sales. Then order equals automodel.order, seasonal order equals automodel.seasonal order, and then to fit our model, we say results equals model.fit. You can see that we will be using parameters that ARIMA found for us. Results equal model.fit. This line of code trained the ARIMA model on the monthly sales data using the optimal parameters provided, and output or results is a fitted model containing information about the model parameters and fitted values. Now we need to generate the forecast. We say that our forecast period will be 12 or 1 year or 12 months. Forecast equals results.get_forecast steps equals forecast periods or 12 months. And mean or average forecast equals forecast.predicted mean. I will also have 3 confidence intervals for my model. So my first confidence interval will be 95, then 80 and 70. Confidence interval underscore 95 equals forecast.conf_interval. Alpha equals 0.05, 0.20 or 0.30. And now we will create visualization of our forecast. Many lines of code just to create our visuals. So first of all, we need to select the figure size for our visual, or plt.figure equals figure size 15 by 7. We need to plot historical data and forecast data. So we say plt.plot monthly sales or our historical data, label historical data, color blue. And we do the same for our forecasts. We will plot mean_forecast, the results we got from our models, then label equals forecast, color red, and line equals 2 because we want our line to be a bit thicker than our historical data. Next one, we will plot our confidence intervals. So we will do fill between, and we will use our 95% confidence interval, 80 and 70. So what happens is each fill underscore between function creates a shaded area around the forecast line based on the upper and lower bounds of the confidence interval. Color equals red, the color of the line. Alpha is transparency of the visual, so higher confidence intervals are shaded lighter. And labels, each interval is labeled for clarity in our legend. Then plt.title x label y label legend, of course, to add labels, title, and the legend to our visual. plt.grid true alpha equals 0.3, again to add a grid to our visual, and transparency to this grid. Then we need to get a final value. So we want to add final forecast values and confidence ranges. This block of code extracts the final forecasted value and the upper and lower bounds for each confidence interval for the most recent forecasted period. And then we will create info text. The purpose of it to show the final forecasted value and the confidence interval ranges directly on our plot. And of course we need to say plt.show to display our data. Let's run it. Okay, that's our final result. So you can see this is the forecasted sales in the next 12 months, and this is our different confidence intervals. And remember, we created this info text, and this is where it is displayed. A confidence interval indicates the range within which we expect the true future values to fall with a specified probability. For example, when we say a 95% confidence interval, we mean that there is a 95% probability that the actual value will fall within its interval. So narrower intervals, when our confidence interval is smaller, for example 70%, it offers more precise predictions but with a lower confidence. And now let's calculate and display all the metrics we calculated. So instead of using the chart, we will just print all of those findings, and it's a lot of them. So I will just copy all these details. First of all, we will print model performance metrics such as mean squared error, root mean squared error, and mean absolute error. Then we will print our forecast information and our confidence intervals. Then we will print interval widths as a percentage of forecast and create our forecast data frame and print those details. So let's print all of that. Mean squared error is the average of the square difference between the actual values and predicted values. MSE penalizes larger errors and more heavily because of squaring, which can help highlight predictions that are significantly off. A lower MSE indicates better model accuracy, while high MSE suggests larger errors between actual and predicted values. If you look at root mean squared error, it brings the error metric back to the same unit as the original data, making it easier to understand. RMSE is often preferred because it is in the same units as the data, providing a more interpretable error value. And same like a mean square error, RMSE penalizes larger errors more heavily due to the squaring process. And then we look at our mean absolute error, which is the average of the absolute difference between actual values and predicted values. It doesn't square the error, that's why it treats the errors equally. To summarize, when you have lower MSE and RMSE, it indicates fewer large errors in the model. So let's look at our data. Our mean squared error is a huge number. It is very high. It indicates that the average of the square difference between the actual value and the predicted value is substantial. If you look at our root mean squared error, it's also very big. It indicates the model's typical error for each prediction. This relatively high error compared to the forecasted value suggests that while the model is making reasonable predictions, there is still substantial room for improvement. And now we look at our mean absolute error, or 14,000. It shows that on average the model's predictions are off by about 14,432. Now let's look at our confidence intervals. So you can see this wide interval of 95% confidence implies that the actual sales will fall between 1,000 and 183,000, and this range is very large, suggesting a considerable uncertainty in our forecast. And you can see with the smaller interval levels we actually get some better results. For example, if you look at our narrow 70% confidence interval, it indicates that as confidence level decreases, the range becomes more focused but still spans a wide interval. This interval suggests that even for a lower confidence level, the model's uncertainty remains relatively high. Let's look at these numbers, which is interval widths as a percentage of forecast, and how you can interpret these results. So the 95% confidence interval ranges nearly 99% above and below below the forecast, meaning that the interval is almost double the forecasted value. So you can see that our forecasted line actually looks alright, but then if you look at confidence intervals, they are all over the place. So there are different suggestions for improvement. For example, data transformation. If the data is highly volatile, which it is in our case, applying a log transformation or differencing might help stabilize variance and improve model performance. If it's possible, you need to add more historical data if it's available. Sometimes it helps to learn patterns and reduce forecast uncertainty. Another way is to apply a different model. We will use a forecasting model, Holt-Winters exponential smoothing, and see how it works with our data. We will test multiple exponential smoothing models with different configurations and see what is the best one for us. First of all, we will create an empty list called models, which will store each of the model configurations. So each of the models we will be using has unique settings for trend and seasonality, allowing us to test various combinations and evaluate which best fits in our monthly sales data. Now we're creating a list called specification that holds various dictionaries, and each of those dictionary has two keys, name and model. Name is a label describing the model configuration, and the model, it is the actual model instances created with exponential smoothing. So as you can see, first is a name of our model, then the model itself. You need to indicate the dataset you will be using for your modeling. In our case, it is monthly sales. Similar to previous model, seasonal period equals 12. This defines the seasonal period, so 12 months for yearly seasonality. Damped trend equals true, allows the trend to decrease over time rather than continue indefinitely. And then we indicate our smoothing parameters. Smoothing level 0.2 controls how much weight is given to the most recent observations for the level component. Smoothing trend 0.1 controls the trend component smoothing. Smoothing seasonal 0.1 controls the seasonal component smoothing, and damping trend 0.98 controls the rate of damping. When values are closer to 1, it creates a less damped trend. Optimized equals fall disables the automatic optimization of parameters, so the model uses the specified smoothing values instead. Trend equals add specifies an additive trend, meaning the trend components is added to each period. Seasonality or seasonal equals add specifies an additive seasonal component where the seasonality remains constant in size over time. If you look at our second model, we can see that our seasonal parameter was changed to mul. This specifies a multiplicative seasonal component where the seasonal variations change in proportion to the level of data. This configuration is suitable if seasonal effects increase or decrease in proportion to overall level of the series. So for example, higher sales in peak seasons. When we had our seasonal equals add, this configuration works well when both trend and seasonality are stable, meaning they don't change in magnitude. And then we have our multiplicative trend where our trend equals mul while our seasonal equals add. This model works well if the trend itself scales with the data, such as an exponential growth pattern, but the seasonality remains constant. Let's run it. Now let's evaluate each of those models. So we will create an empty list called results, and then we create a loop. So for spec and specifications, we just adding model and a name, and then calculating metrics such as root mean square error and a mean absolute error. And then we'll just append all these results and see what we've got. Now we will find the best performing model from a list of models based on their root mean square error. So we're creating a new variable called best model, which equals mean out of results, and results is our list of dictionaries where each dictionary contains information about specific model, including the model itself and its performance metrics such as RMSE. Next line of code, we are assigning the best model to a variable called HW_model. So the best model retrieves the actual model instances from the best model dictionary. Our variable HW_model, the variable now holds the best performing model, which can be used for our forecasting. And then we will do forecasting for the next 12 periods. Now we will again create visualization. It's a very long code. So plt.figure, we're selecting our figure size, and then we are subplotting all our models. On the first chart, you can see the comparison of all Holt-Winters models. Our dark blue line is a historical data, and then we have our 3 models. And based on our analysis, the best model forecast is multiplicative trend. This model works well if the trend itself scales with the data, such as an exponential growth pattern, but the seasonality remains constant. And it's actually the truth what we've seen in our data, because yes, our revenue was increasing, but the seasonality pattern was the same year after year. And here we have the visualization of best model residuals. And now let's print all the results of all our models to see if it really works better than our ARIMA model. So this is our fixed parameter, and now we have results for our 3 models. Let's print the parameters for our best model. Let's look at our model comparison. You can see that this model, or multiplicative trend, performs the best. It has the smallest RMSE out of all other models. However, I can say that all of those 3 models actually performed very well. For example, if you look at our fixed parameters model has a relatively low RMSE and MAE, suggesting it predicts data fairly accurately. Let's look at the results of our ARIMA model. You can see that root mean squared error is 19,000, while mean absolute error is 14,000. If you look back at the results of this new Holt-Winters model, our RMSE is 9,000 compared to almost 20,000. So we significantly improved the accuracy of our model. Here we printed parameters that are the best for our model, what our smoothing level, trend smoothing, seasonal smoothing, and damping parameter. And if we want to print our forecast results, we can say HW_forecast. Let's print it. Of course, you can use dot ahead to print top 5 rows or dot tail to print bottom 5 rows. And this is the forecasted result for each of the months. And the last lines of code, we will save the results of our model. We are creating a new data frame called a final results, and this data frame will organize the actual values, fitted or predicted values, and residuals from the Holt-Winters model. So our actual is monthly sales, or the dataset we were using for our predictions. As for fitted, this column holds the fitted or predicted values generated by the Holt-Winters model, and it's useful because we can compare our fitted values to the actual values, and it helps to assess how well the model captures patterns in the training data. And we have a column residuals. This column contains the residuals, which has a difference between the actual values and the fitted values. And if we print our final results, you can see that for some of our months the difference is very small. Our predicted value is very close to the actual value, while for others, unfortunately, we have a very significant difference. That's it for today. There are different models that can be used for forecasting. For example, XGBoost is a great algorithm to be used for time series forecasting, and maybe if you are interested, we can use that model next time. Please let me know in the comments. I hope you enjoyed this video, and I hope to see you next time.